There are two primary methods of inference. The first of these is a hypothesis test. The second is a confidence interval. We're going to look at confidence intervals in this video. A confidence interval bounds a parameter within a range with a specified level of confidence. Let me give you an example. Suppose we say we are 95% confident that the mean, that is the parameter, the mean, is somewhere between 47.2 and 53.7. This is a statement about the mean of the population parameter, and we make this statement with the specified level of confidence that is used when constructing the interval. It's interesting that we can take observations from a sample, calculate a sample mean, and from that, there's a technique to produce a confidence interval for the population mean. This is true no matter how large our population is. The level of confidence is inversely related to hypothesis testing risk. So if we have a type 1 error rate set at 5%, our confidence level is 1 minus this type 1 error rate. So for 5%, it's 1 minus 0.05 or 0.95, which we can say as 95% confidence. The confidence interval is the set of all retained hypotheses if we test all possible hypotheses using two-sided hypothesis testing. What you're seeing here is that the two methods of inference are related. A hypothesis test is a test about a single population parameter value. A confidence interval is a test about all possible values for the population parameter. So in essence, to create a confidence interval, we are conducting many hypotheses tests. Let's take a look at this using an example. Suppose that we obtain the GRE scores for 64 randomly chosen education students who took the GRE. Further, suppose that the average of these GRE scores is 147. We would like a 95% confidence interval for the population mean. So here's the setup. We know that the population of GRE scores for everyone who takes the GRE has a mean of 150. We have a sample of students who are from education who took the GRE. We would like to know, what if we looked at the population of all education students, not all GRE examinees, but all education students? What would be the mean of that population of students? Well, that population is still too big for us to examine, even though it is only education students. So we need to take a sample from that population. We have done so. We've obtained a sample mean of 147, but from this, we would like to create a confidence interval for the population mean, the mean of education students' GRE scores. The sampling distribution, we say under the null hypothesis, meaning when the null hypothesis is true, is going to have a mean that's the same as the mean of the population of scores. We're going to be changing that mean to be different values. Remember, to construct a confidence interval, that we have to test all possible means. So in this sampling distribution here, I have left the numbers off the x-axis because they are going to change depending on what our hypothesis is. Whatever we hypothesize is going to be right in the middle of that distribution. The standard deviation of means, however, will still be 8.75, which is the standard deviation of GRE scores, divided by the square root of n, in this case 64, which gives us a standard deviation of means of 1.1. So as we change the hypothesized mean, this distribution will move to the left or the right. It will move up and down, but the shape will not change. The variability will not change. So here's our first null hypothesis. I'm just going to try a guess, and I'm choosing a guess of 150. That seems like a reasonable guess for me to make because that happens to be the population mean for all GRE examinees. If I put in a population mean of 150, look at my sample mean of 147, and look where that 147 fits on the distribution, the probability of getting a score less than 147 is 0.00305. I need to do a two-sided test or a two-tailed test, and therefore I need to multiply that by 2 in order to get my p-value. That gives me 0.0061. Remember, the rule is that if the p-value is less than alpha, which in this case is 0.05, we will reject. We will reject 150. That number will not be in our confidence interval. So now we need to make another guess. Let's try a guess of 149. This time, the probability of having a score less than 147 when the sampling distribution mean is 149 is 0.0337. If we multiply that by 2, that's 0.067. This is above our alpha, our type 1 error rate of 0.05, so we retain the null hypothesis of 149. 149 will be in our confidence interval because we retained it. Now, knowing that 149 is in the interval and 150 is not, is going to help with our third guess. I'm trying to find the cutoff between where I reject and retain, and it's going to be somewhere between 149 and 150. So let's try a guess of 149.5. This time, the probability of obtaining a sample mean of 147, which is what we obtained, the probability of that or less is 0.0111. Multiply that by 2, and that's 0.0222. That is less than alpha of 0.05. So 149.5 will not be in our confidence interval. Let's try 149.1. This time, the probability of being less than 147 is 0.0274. Multiply that by 2, 0.0548. That's greater than 0.05, so 149.1 will be in the confidence interval. Let's try a guess of 149.2. This gives us a p-value of 0.044, so we reject the null hypothesis because 0.044 is less than 0.05. 149.2 will not be in the confidence interval. We found that 149.1 will be in the interval and 149.2 will not be in the interval. So we found the boundary. We have found the boundary between rejection and retention. That means we found the upper boundary of our confidence interval. Now I have to go to the other side to look for the lower boundary of the confidence interval. Notice that I've been using hypotheses that are above 147, my sample mean. Let's try some hypotheses that are below 147. How about 145? Since the sample mean of 147 is above 145, I'm going to switch now to the upper tail in order to see if I reject or retain. The probability of getting 147 or more when the true mean is 145 is 0.0337. Times that by 2, we get a p-value of 0.067. We retain the null, so 145 will be in the confidence interval. Let's try 144.8. This gives us a p-value of 0.044. That's less than 0.05, so we reject 144.8. Let's try right in between 144.8 and 145. Let's try 144.9. That gives us a p-value of 0.055. We retain 144.9. So we rejected 144.8 and retained 144.9. We have now found the lower boundary of our interval. So let's put this all together in a confidence interval. We are 95% confident that for education students who take the GRE, the population mean, not the sample mean, we know that's 147, but we can infer from that sample mean of 147 that the population mean is between 144.8 and 149.2. It bears repeating that we only had a sample of size 64 and the population could be thousands. Yet we are able to make inferences about that population mean even if it contains thousands of students, as long as we randomly sampled those 64 students from that population. So now we have looked at two inferential statistics, p-values, which are calculated from a sampling distribution under the null hypothesis. They're used to make a decision about the null hypothesis, and they lead to inference about a single value of the population parameter through a single hypothesis test. Or confidence intervals that are calculated from a sampling distribution under the null hypothesis, just like p-values are, but these are based on decisions about every possible hypothesis, and they lead to more specific inference about the population parameter. In the view of statisticians in the modern era, confidence intervals are highly preferred to p-values. I hope you see why. A p-value allows us to make a decision about a single proposed population mean. A confidence interval actually tells us what that population mean is.